mathematics. So thanks for bearing with me up to this point. Today we will try to connect to physics from that point, but we need to add a little bit of information to really finish this mathematics block and wrap it all up. But before that, let me recapitulate the essentials of yesterday's discussion. Actually, there's not so terribly much you need to remember. So we were arguing that given some kind of symmetry group, we can always manage to bring our effective Hamiltonian representing our system into some block structure, right? So we were dealing here with kind of blocks of 1, 2, 3, and maybe so on. In the simplest case, where there are no symmetries, a priori no unitary symmetries around here, it's just one block, perhaps. And that was, I mean, as much as we could say in generality about the unitary symmetry contents of the theory, and these blocks had finite dimension in 1 and 2 and 3 respectively. Right? And then we were starting to consider time reversal, the anti-unitaries on top of that. And we said that there are essentially 1, 2, 3, 4 options to consider. The first is there is no time reversal to talk about, and we are basically stuck with this. That's what I want to say. The time evolution in this case is unitary, right? So no time. And we can always, we manage to bring our manifold describing our time evolution in the book. Most general case will be UN or some substructure thereof. Now, if we have time reversal, then it kind of have an anti-unitary operator operating on this structure. And we said there are two options, namely time reversal can be such that it warps you from one sector to Hilbert space to another one, say from this block to that block. And it happens, and keep in mind, I mean, the quintessential example I mentioned was some kind of structure, some kind of low energy quasar particles, if you want, defined in some momentum type landscape, where you have here a little low energy island and maybe here. And time reversal, we know, reverses momenta, so you get warped from this little Hilbert space to that one. And this would correspond to such a mapping. In this case, we by and large remain unitary in a sense. Yeah? We argue that in this case, one of these unitary dynamics is free, but the other one is then enslaved by time reversal. Yeah? And we had this discussion of how it works out. So that is the second. That is the second scenario. The first one is no time reversal, and in the second case, we had a situation where basically we end up with block structures U, and then we have this fancy notation tau U inverse. But the essential point is this one is free, that one is enslaved. It's still unitary. So we are still in this setting. The third scenario was, and then it started getting more interesting, when time reversal actually is compatible with the Hilbert space decomposition when it respects the block structure. And in this case, that's the third scenario, if you want. So time reversal remains in this block. In this case, we actually had to discriminate between two options. The first of these was time reversal squares to 1, or it can be the operator representing time reversal can always be brought into a form where it squares to 1. And that's appropriate to the description of integer spin quantum systems. So we had this t squared equals 1, in which case our Hamiltonian can be chosen symmetric or asymmetric if time reversal is modeled as complex conjugation. And well, now the question is now what is M? So being symmetric is the opposite of being antisymmetric, right? So what we do is we take all our unitaries, matrices, and divide out those we don't like, namely the antisymmetric guys. And unless you force me, I will not go into more detail of how to can think about. But that would get a bit dry. I mean, how to represent this data. But you get the drift, right? These are. Think of time evolution is simply e to the I symmetric matrices, and that's exactly this. Okay.
So, can I just understand that UN over ON is removing all the antisymmetric part from the UN?
Yes, exactly. Yeah, precisely. By definition, exactly. And 3b is t squared equals -1 half integer spins, in which case its situation is a little bit more involved. Time-over symmetry in the canonical or simplest representation amounts to transposition and then conjugation with, you can write here. Yeah, I mean, we can do it like this with a parametric sigma y. Yeah? And, in this case, m equals un. And now you also have to divide something. So what we removed here, this on, can be was simply the set of unitary matrices uns, which have the property that they are these were the ones we wanted to get rid of. In complete analogy, here we want to get rid of the subgroup SPN, compact symplectic group. Yeah.
Sigma y acting in what subspace?
In the subspace, when you write T equals some unitary K, this unitary can be chosen as I times sigma y. And the sigma y in a natural way, so in a spin 1/2 system, will act in spin space, spin up, spin down.
Yeah, I guess I understand it for spin, but what is it? What is this 2x2 space in general?
You can, in this case, but you can always arrange your Hilbert space in such a way that your anti-unitary time evolution gets you from one block of Hilbert space to the other one, and that then defines the structure. I mean, a grading in which your sigma y acts.
It always has a structure of like a spin and a half times another space.
Isn't that Kramer's?
Yeah, they agree.
Yes?
Kramer's pairs or something? Kramer's pairs?
Yeah. So you have a natural pairing in this case of T squared equals -1.
But you're probably going to use it as BCS, whatever, particle holds.
No, BCS, why BCS?
Are you going to talk about superconductor?
Yeah, but then then we will not necessarily talk about, I mean, we are not there yet, but so the SPN is now, this symplectic group, the definition, is U transpose equals sigma y. So in the same, everything the same, only that you conjugate by this antisymmetric matrix that defines the symplectic group, compact symplectic group, and I mentioned, and we want to get rid of that one. Now, if you feel a bit uncomfortable about the symplectic and this conjugation and so on, it's perfectly fine to focus on this sector here, right, for the purposes of these lectures. I mean, I mentioned this in passing to make the story complete, but don't worry too much about it.
Just a question of terminology. I know this 3B as the symplectic case. Now, if we remove the symplectic, if we take U and remove the symplectic group out of it, it seems like a funny name.
Yes, indeed. There are lots of funny names in this game. Symplectic ensemble, symplectic invariance. And okay, maybe one remark historically. I mean, there was, for example, you can get confused because you ask yourself, what is the maximum invariance group preserving this condition? It will be the symplectic group, that's how we rid of it. I mean, it's all a bit confusing. And that confusion is I mean, I don't want to talk about it too much here, but historically responsible for the fact that out of 10 symmetry classes, which there are, only 3 have been identified by the mid-90s. Because if you emphasize aspects like this invariance, then you will easily miss the other 7 guys. And that's why I'm stressing so much, with benefit of hindsight, this structure here, the maximal, the manifold that accommodates time evolutions. Because once we are here, as you will see in a few minutes, it's very natural in a unique way. We anticipate that there must be 7 more besides. And this was not seen by Dyson because he did not. But it's a bit cryptic maybe what I'm saying, but we come here. Yeah?
Sorry, I missed it. Can you clarify? I missed something you said. So 1 and 2, well, let's say 2,
Yeah.
t squared to minus 1, or I don't understand the relation between 2 and 3, let's say. So in 3, you're talking about, you're not even mentioning the blocks. Let's say U1 and U2 blocks. But
Yeah.
It stays in the same block?
it's all in the same block?
No, here you have a unitary, you have one unitary block.
Right.
And time reversal, switches between these.
Right, okay.
In the other case, you stay in one block, time reversal, and then you get an extra condition. I mean, in a say, these 2 conditions merge, but they now are defined for the same block. And so you have to impose this extra condition to be compatible.
Oh, I see, okay. So it's all one block, is 3.
For example, what you can do is if you have this kind of structure, I mentioned here, right? If you introduce some time reversal preserving impurity scattering, which gets you from here to there, then you no longer have, your Hamiltonian has no longer 2 separate blocks, they get now connected by impurity scattering matrix elements. Now all of a sudden you have one big block.
Oh, I
And
see.
in this one big block, you can then always impose this condition. So you go totally some time reversal invariant to describe it in terms of this invariant. Yeah.
So I think I want to repeat the same question that was already asked. But so what is this grading structure there? So in case of spin 1/2, it's more or less clear. But in general, this the grading that the sigma 1 acts on.
I guess I want to say, and to be cautious, you can always, for given Hilbert space, with t squared equals -1, you can cook 1/2. And I'm not even sure whether it's unique.
So there isn't some canonical way.
No, nothing is canonical here. In this, because this is all up to unitary transformations. You can always switch a basis. Say, if in you have a time reversal invariant Hamiltonian, in this example, and it looks symmetric in one basis, it need not look symmetric in another basis. There always is a basis where you can have it. No? Yeah.
Just to clarify notation, where you write t is equal to uk, are you imagining here that u is equal to I sigma y?
Oh, that is a different view. That is some unit. Yeah. I sigma y is unique. Maybe I didn't get the question.
No. Just, I think yesterday you said that you're picking u to be I sigma y. as
Right,
the
exactly.
unitary. So here really I could replace the sigma y's by any unitary that sits in the time equation, right?
First of all, this view is not that view, right? I mean, this
It's
is
not that u, it's the sigma y.
It's a sigma
I
y. Yeah. Yes. I mean, let's not call it this. Let's call it what it is. I sigma y. Yeah.
So it's how I write my time reversal operator that tells me how I create this symplectic.
Yes. Okay. So that's one way of kind of, putting the. Now let me now summarize what we have so far in one kind of table, and that will give us some hints as to how to proceed in what to do. So summary, we have physics dictating symmetries, and in the parlor of this field they are called unitary. These would be the options 1 and 2. Orthogonal, because there is some orthogonal group floating around in the game. And symplectic. They are distinguished for their behavior under time reversal.
Vector
three examples, or the four examples you gave are which in this? You said 1 and 2 are unitary?
1 and 2, 3A, 3B.
3A, 3B.
Time reversal nil here. Or, nee. I don't know how to write 1 and in 2 it's okay. Like such. In the orthogonal, I have time reversal invariant here as well. We can ask ourselves what t squared does. Here we wouldn't even ask the question, who cares? Here it is 1, and here it is minus 1. Then a bit of terminology. I mean, it's simply for labeling things. The way I want to denote these, or distinguish these different cases in view of what we are doing later when more symmetry classes enter, we call this here tau nil, tau 1, tau minus 1. Just some labeling. Yeah? Then there was this invariance, this maximal manifold of time evolutions, un over on to n over spn. And one final bit of information, which is maybe there more for historic reference. Historically, people were asking, given a Hamiltonian, what is the maximal set of basis transformations that preserves its symmetry structure? And that's easy to answer. It's here, it's a unitary group. Transforming this by unitary remains unitary. Here it is the orthogonal group. A symmetric Hamiltonian transformed by orthogonal transformation remains orthogonal. And here it would be symplectic. And that's why they are often called unitary orthogonal symplectic ensemble or symmetry class work. Now,
If we perform a unitary transformation on the Hamiltonian with a symplectic group of no longer is invariant,
it will you no longer have this kind of representation if you apply general unitary.
because then, but if you then choose a different,
Yes, then you disguise your symmetry, right? You can of course say, I have this Hamiltonian, it's somewhere invariant, but now for whatever reason, I do a global unitary transformation. Time reversal is still there, but it's now disguised. It no longer. Transposition, when you see transposition or complex conjugation, it's always a hint that there's heavily basis-dependent operation, as opposed to Hermitian adjoint or.
Could you clarify what you mean by this invariance? Like, shape of the subclass?
Yes, we want to work, suppose here, we want to work in this nice representation for all times. I mean, and then we ask ourselves, what is the maximal freedom we have to in our choice of basis so that we remain in this sentence? And would be the orthogonal sample. If you transform this Hamiltonian unitarily, you're no longer able. More like a matter of convenience.
Question? Or what is tau?
Tau is the operation of time reversal as acting on operators. Just call it tau. And I use these symbols here, these are formal symbols, to discriminate between the cases. There is no time reversal, there is time reversal squaring to 1, time reversal squaring to minus 1. It's just a bookkeeping.
But in the unitary class, you had the one case where there was time reversal symmetry.
Exactly. Yeah, I'm overstretching this. Let's think about it like this. Let's pretend there is no time reversal and focus only on this block.
So you're specifically talking about time reversal within the block.
Yeah. When you can always add then. Suppose you can think about it like this. There's no time reversal.
Okay.
But now let's add, for whatever reasons, a time reverse partner somewhere in outer space.
Okay. And in the second, in case 2,
Yes.
time reversal could still square to minus 1. Could it?
No. Complex conjugation.
No. The second case, number 1, number 2, that one.
Oh.
It could, right?
It could, in principle, yes.
Okay.
It can, yeah, sure, of course. There's sub cases there. I mean, yeah. But I think it's already complicated now.
And hypothetically, could we not look up multiples in house?
Nice question.
So we don't have just one spin half space, we have multiple
Of
spin
course,
half spaces
sure.
across one?
Yeah.
And then would these partition further?
Yeah, time reversal will always get you, I mean, will be involutive. I mean, you get from one space. No?
So in case 3, time reversal is operating within the spin space,
Mm-hmm.
right? And I could say it's swapping blocks in the spin space.
Yes.
But that I'm treating as special. So I do coset space, UN, ON, and so on. So why should I not play the same games in case 2?
Do you want to consider a case where the spin sectors, spin up and spin down, are coupled by the dynamics or not?
I'm thinking of the case, for let's say case 2, the 2 blocks actually refer to spin up and spin down. Somewhere
Yes.
disguised.
Yes, yeah, very good, yeah, correct. Yeah.
And then case 2 is actually case 3 in disguise.
No, it's not. It's a very special, it's a sub-scenario. I mean, it's tempting to mention an example of topological insulators, but I'm hesitating. Could I? So maybe it's happening. I mean, think of a spin quantum Hall effect, my favorite example. So you have a 2D edge, a 2D system, and here you have edge modes. And there are counter-propagating modes, that's what they teach us. And one is spin up, and the other one is spin down. So now you can say, aha, that is actually more or less this setting.
Right.
And it indeed is. You have 2 unitary counter-propagating theories. Neither is time reversal invariant. However, the moment you have, this presumes rotation invariance around the spin axis.
Right.
Now, if you add scattering between these spins, so that the spin U1 is no longer preserved, then these 2 blocks merge on the level of the native Hamiltonian, and they become one 3D plus 3D block.
Got it.
Yeah. All right. Now, these guys here are known to mathematicians, and they have a name for them. They call these symmetric spaces. And so let me say a few words about these symmetric spaces. These are particular examples of symmetric spaces, and they go by the name A-N, A1, N, and A2, N. Kind of creative notation. And he knows what is called the rank of the symmetric spaces, that dimension of object. Right? Now, what are symmetric spaces? Symmetric spaces are mathematical objects. And again, unless I'm forced, I will not define them. I will just tell you in some prose what they are, right? If that is okay. So the symmetric space, you can approach this mathematical structure from 2 different perspectives. I mean, there are 2 different kind of definitions. Number 1 is a symmetric space is a smooth manifold. I mean, there's lots of smooth manifolds around. But it is a smooth manifold with some extra structure. First of all, it's a Riemannian manifold, so you can measure length. Yeah? And then it's a particular Riemannian structure, a particular manifold where you can measure length, namely one that looks the same from all perspectives, and hence it's called symmetric. So you can make this much more precise, but then you have to talk about geodesics and so on. But think of a sphere. A sphere is a nice example of a symmetric space. It's Riemannian and it looks the same from all directions. Right, and I mean that is, I mean, and these qualify in this sense. These are Riemannian spaces. You can define a metric on UN, and UN looks the same no matter from where you look at it. Then there's a second definition of symmetric space, a second approach, which is more algebraic. Yeah.
So you said looks the same. Is this in the meaning of the invariance you mentioned?
No, in the meaning of forget about the group structure for a moment, and just look at UN. And I mean, there is no preferred frame in UN. I mean, you can make this quantitative. You introduce a metric, you introduce geodesics, and then you say that there are some inversions and so on. You can spend a lecture on that. It's just heuristics. I'm throwing the heuristics at you. Yeah.
maybe a stupid question, but are Lie group manifolds Riemannian manifolds?
Yes.
Symmetric spaces?
Yes.
Okay.
Well, I mean, not every, classical Lie groups are symmetric spaces, yes. Yeah.
Just briefly want to come back to this issue, just to clarify things for me. So let's consider graphene, say. It has true spins, t squared is -1, but it also has values.
Yeah.
And time reversal swaps the
Exactly.
two values, so it's case true.
Yes.
But if I introduce disorder now, I'll have scattering between the two
Yes.
values. So am I not now in case 3 for values as well?
Yeah, in graphene, how does it go? It's either one of these here.
Right. So I have t squared is -1 for spins and t squared is +1 for values. And so there's a more complex structure.
You can always reduce this to this one. And for graphene, I even thought about it some years ago, but it's just my readout problem in memory. What I should keep an eye on the time because I mean it's very interesting, but also somewhat involved question. So I was about symmetric space manifold with no preferred, looking the same from all directions. Then there's a second approach which is more algebraic, and that one tells you that symmetric spaces are either the classical Lie groups, U or O or SP, or coset spaces thereof, right? And what you can show, what mathematicians would tell you, spend a whole lot of time on that, to show that these two approaches are equivalent. I mean, this group-oriented and the Riemannian manifold-oriented. All that is kind of to convey the idea of what a symmetric space is. One more thing, if you have a Riemannian manifold and it looks the same from all directions, then it has constant curvature. Right? On a Riemannian manifold, you can introduce curvature. For example, the sphere is global curvature 2 everywhere. Now that curvature can decide whether it wants to be positive, 0, or negative. If it's positive, then we are dealing with a compact symmetric space. I mean, positive curvature, and these here are nice compact symmetric spaces. If it's 0, then we are dealing with an Euclidean space. That's boring. What's linear algebra? If it's negative, then we are dealing with a non-compact symmetric space, like a hyperboloid would be an example of a non-compact symmetric space. Yeah. Okay, so that's all. Maybe not. You can ask yourself why I'm telling you. The interesting piece of data is this: there's only 10 different symmetric spaces. There's 10 fundamentally different classes of symmetric space. I mean, you could think there are zillions of different options. No, there's only 10. Or I should say 10 families, and these families are indexed by their rank. So you have 10 families of compact symmetric spaces and 10 families of non-compact symmetric spaces. And they were classified by Cartan long ago. And Cartan also introduced, let me expose it. Actually, it's quick to ask you to write. So there is the Riemannian geometry approach. And the buzzword here is that we're dealing with a symmetric Riemannian manifold. Is that okay once and for all? Yeah. And hence we have constant curvature. That's one corollary of that. Then there is the algebraic approach. And that will tell you there are classical Lie groups or quotients. So, I just O(n), or maybe something like U to n over UN times UN, particle physicists like that space. And there's 10 different options here. Now, there is a Cartan classification, and he gave these names. And these names are, like you see some of them here. So they go by the name A, or A1, or C, B, D, 10 different symbols, no order or systematics I could identify. It's like in that, and you just have to learn them if you want. Good. So that's, and what this tells us here is that 3 of these symmetric spaces are in a very natural way realized as time evolutions of quantum mechanics. That's what our so far discussion showed. But then you all know that, well, stupid way of saying, but when nature has an option, it tends to max it out, right? So what about the other 7 guys? Are they forbidden or not? And so that's a natural question to ask. And one conclusion we will reach is that all 10 of them are realized as unitary time evolutions of quantum systems. Only you have to go to quantum systems with a little more structure than those, and we will get there, superconductors. Yeah.
You just said that nature is the option and it will try to fulfill it. So what about exceptionality groups? Is it conceivable that they also realize the nature?
I don't know what the exceptionality groups, whether they are, it's a wide field in my education. The only thing I know is that there's 10 compact symmetric spaces, and those happen to be the classical.
But doesn't have to do with an arbitrary rank.
Huh?
Maybe these are the only ones which could be of arbitrary rank.
Yeah, could be. Like I said, white flag. Nothing. Yeah.
But again, so what are the symmetric space defined by this quotient, defined by the G and H?
Yeah, but sometimes H is unit group, and then we have just a group like such, and you don't divide out anything.
Right, but you simply you divide by UN cross UN?
That can also happen, yeah.
But
you will not be able to see any systematics here.
No, but I'm trying to just identify that, what you wrote there, to what you wrote on the M column when you nettleboard.
Yes, that is symmetric space A, which is what it is, UN. Then we have A1, which is UN over ON, I didn't write it here, and then there is A2, which is UN over SPN.
Well, those guys are the quotient, that's the H.
No, that here is A3, which I haven't mentioned so far. Just another one. These are just examples.
Okay, so
there is no systematics.
But
here
that
or
would be
here.
one of the 10.
Huh?
That's the last one is one of the 10 that you haven't mentioned.
Yes, exactly. Okay. It's A3, and it's a very nice one. We will get there. We'll make friends with it. Yeah.
So far, the observation is that the manifold of are represented by given by 3 different symmetric spaces. And it is then just a guess that all time evolutions should be some symmetric space, and because there are 10.
Yeah. No, well, that you can actually prove.
That they are.
What you can, right? That you can prove out, but I'm not sure how to prove it. Whether could you think of some time evolution which is not a symmetric space? You see, it's like with Alex. I never even thought about the other Alex. It's so natural that maybe you will agree or not agree at the end of these lectures, but it's a natural setting for time evolution.
And if you include the non-compact one, does the naming convention make any more sense? Or
no. Maybe to mathematicians it may make sense, but not to us.
The non-compact ones don't come in here.
They will. They sneak their way into the story.
They will. Okay.
Yeah. Okay. To anticipate a little, one need not even emphasize the symmetric spaces too much if it was just about symmetry classes. But then at some point we need to describe the symmetry class in terms of operational tools like diagrams of field theory or transfer matrix and so on. And it so happens that these are all field theories in some sense. And field theories have a target space. They are field theories like spin has a target. And these target spaces are again symmetric spaces. So there will be duality. There will be each symmetric space realized in your Hamiltonian language will have a partner symmetric space in whatever tool you like to apply to it. And some of these are non-compact. If you do supersymmetry, for example, you have to combine compacts and non-compacts. Or if you do transfer matrix approach to this or that wire, then you have to work with non-compact symmetric spaces. But in nature, because nature is unitary time evolution, it's only the compact.
Can I think of?
Can
I think of compact as non-compact periodic boundary conditions versus open?
No,
Just
no, no.
you go, you return to the same place. So.
No, it's not about boundary.
I mean, not about boundary conditions, but basically compact space means that if you go somewhere around, you end up in the same place again in this space, or why can we only have compact?
Because time evolution is a compact manifold, subset of the unitary group. It gets more non-compact when we start talking about bosons, and yeah. But I mean, within this framework which we're operating, it's all living in the unitary group. I mean, we're confined to the unitary group. Yeah.
So, sorry, that was just disturbed a little bit by the vagueness of the definition of symmetric space. And I mean, okay, so we have some group, that's a group, it acts on something. Can you phrase some condition, whatever vague, of the type that, I don't know, this acts on itself, I don't know, by conjugation or something, and something is preserved?
I can give you, you have two options. You can force me to spell out the precise definition. That will take more time. Or you accept the following, which is another way. If you have such a Riemannian manifold, under the conditions where it is a symmetric space, then you are given, it's a bonus, a symmetry group operating on this manifold.
Okay.
And these symmetry groups are those here before you start factoring out. And
so it's a UN acting on UN, say, cross ON. Or
it's a UN acting on your manifold. Mm-hmm. But then occasionally you remove something which is a stabilizer of some involution, and this involution is exactly how. What I suggest, if you're interested, let's discuss it in private, perhaps. I mean, I'm happy to discuss all this in as much detail as I can, but it's getting too mathematical.
A small non-mathematical question. Why should time evolution, under various restrictions, be a symmetric manifold? Any reason why?
No, that's, the symmetry aspect here comes in because we're talking about the maximally allowed ones. So apart from symmetry, we have no information to talk about. Right. So there is no preferred frame, no basis that is preferred.
I see.
So it's totally blind to any kind of structure which would spoil the symmetry. Okay, so now I want to connect from this here to more physical. More physical discussion, yeah? And what I want to discuss with you is how do these symmetries, if they are present, manifest themselves in the ultra-ergodic regime of quantum systems. So the setting is now, think of your favorite quantum system, but only put fermions there, fermions. And think of a situation where you have hard chaos and you have a compact energy shell and gives the system all the time in the world, like a heavy nucleus or a quantum dot with some electrons in there, and give them 5 minutes to relax. We learned yesterday, they do not relax, but they let them explore, classically thinking, their energy shell. And then we want to ask the question, what can we say about this system, such a system, from a quantum perspective? Can we say anything at all? And how does it connect to symmetries? Yeah. And the first part of this discussion will be totally qualitative. So the connection is now symmetries and ergodic regime. So let's do the following Gedankenexperiment. I mean, we take a little piece of metal, and there are some impurities in here, right? And now we ask what to do with it. And since we have no good idea, we take the Hamiltonian, diagonalize, and complete the spectrum. Pretty much the first thing I might do. So we diagonalize our Hamiltonian numerically, and what comes out is a spectrum. So something like that. We have here an energy axis, and on this energy axis we have levels. So there's many more levels here, and here we just look at a portion of the spectrum. Now if we stare at this, what comes to our mind? I mean, first of all, we notice there is some typical average spacing between these levels, yeah, that we can identify. So there is some scale which would identify if it's a typical spacing between levels. One thing that also springs to your eye, if you look at the spectra of a chaotic system, is they look curiously regular. I mean, if you look at the integral spectrum of the integral system, they look much more disordered. I mean, in general, there could be groups of multiplets, and atomic physicists will tell a lot about, I mean, here's something, but there are huge gaps, not so in chaotic systems. They are usually rather regular, but that's the only thing we can say with our naked eye. And that's as far as we can get. I mean, we can, of course, communicate this information to somebody and telling them about the positions of the levels, 10,000 levels, but it's not too rewarding to do that, right? So, lacking better ideas, we could do the following. We could play a little bit with the position of our impurities, maybe shift 3 of them to different positions, and run the same game again. We get a different Hamiltonian now, which is microscopically different, macroscopically the same system, and we diagonalize that one as well. So, again, get a spectrum which looks qualitatively the same, but the levels have, of course, changed their position. And often it takes rather small manipulations here to get a rather strong change here. That's another manifestation of chaos. There are sensitivity to boundary conditions in a way. Okay, so now again we think, what should we do with that? And long ago, in the 30s of the last century, the idea came now up to not so much to focus on realization-specific data, but rather to ask, are there statistical properties of this spectrum? So to run this statistic approach. In the following sense, you can, by playing here with whatever system parameter you want, system geometry or impurities, you generate a whole ensemble of Hamiltonians. So you have here some kind of microscopic parameters. Whatever you like, it doesn't matter which one. And as a function of these parameters, you generate a family of Hamiltonian. Now we have a whole ensemble of spectra to talk about. And now we can start asking statistical questions. And that, I mean, given that there is some kind of similarity between these spectra and that there is this kind of stiffness, actually suggests that this could be a good approach. And how would you formulate such a statistical formulation? The first thing, that's one way of attacking the problem. The first thing you might want to do is you identify some observables that are good in classifying or describing what's actually going on in this spectrum. For example, the simplest observable you could focus on would be what is the density of states in your spectrum, which is of course delta value here on average. Yeah? So we identify an observable rho of E, which is nothing other than 1 minus 1 over pi, imaginary part trace of the retarded Green function. And the retarded Green function is E plus minus 8. And this is a trace over our Hilbert trace. But now we consider the average. And averaging here is over the ensemble of our Hamiltonian. You could do this numerically, such an average. Yeah? So we look at this. That would be a nice, but not too interesting observable to study. The next more complicated one which you can think about is maybe this one. You fix a certain energy, and then you ask about correlations in the density of states here with the density of states a little bit further on, right? So we identify here some spacing, call it epsilon, and compute a pair correlation function between density of states E and E plus epsilon respectively. So that's an observable which in the jargon of the field is often called R2 of epsilon. It's historical denotation. And it is defined as the average correlation between rho of E and rho of E plus epsilon. again, averaged over the ensemble. And if you look at the typical characteristic portion of the spectrum, such a quantity does not depend on the center energy, but it will sensitively depend on epsilon. So there is stuff like that you can compute. Now, if you do that, I mean, if you do that for numerically, for a given system, and then you will discover a striking degree of universality in these correlation functions and all others of similar flavor you could construct. There is a huge amount of universality, which can be summarized as follows. The correlation functions, statistical correlation functions, will be defined in this way. Depend on. Typically, they depend on one-dimensionless parameter, namely this epsilon here. You could think of higher order correlation function, but you have some energies around in units of the average level spacing. That's the nature of parameter, which is in the game. Parameter. And epsilon over delta. They do not depend. Okay, I mean that's what I'm. Yeah, they also depend on the symmetry of the Hamiltonian. Namely, on whether we are in situation A, A1, or A2, for example. So the functions you will see on your computer will sensitively respond to the symmetry class in which you are. They do not depend on all kinds of details. I mean, like dimensionality or whatever you could think of. I mean, this is basically the only piece of information you get. And then you get another striking third feature, which is perhaps the most important of all. You can run this kind of program for one type of system, say quantum dot subject to some disorder, and you will observe these nice functions, and you can write a paper and see here they are. But now you could take an entirely different system, which, however, should again be an ergodic quantum system in the sense we specified. For example, a heavy nucleus, or a complex molecule, or whatever other system you like, and you will obtain the same functions numerically. I mean, the same. Just saying. I mean, so the functions you will see on your computer after appropriate rescaling, if you rescale your data such that all of these systems have the same data. I mean, nucleus, of course, has different data, but if you rescale and work in this parameter empirically, you always find the same correlation function for all chaotic energies. Yeah.
These are all zero-dimensional systems.
Zero-dimensional, yes.
So that's right.
No.
The dimensionality doesn't come in.
We call them zero-dimensional. In this sense, they are of course higher dimensional. They are three-dimensional, two-dimensional. They are zero-dimensional in the sense that we went to timescales below the excitation gap of the Perron-Frobenius operator. So they are ergodic. And in this sense, zero-dimensional. So I mean, in hindsight, we have all heard about that. I mean, there is universality, but it's actually a striking phenomenon that all these ergodic systems have the same functional dependence of statistical correlation functions in spectra, but depend on system type. And yesterday we learned that an individual of these systems will never thermalize in a quantum sense. They discuss it. So the question is, can we still say something useful or not, something universal? What it thermalizes in this sense. The system relaxes, and once it's relaxed, its quantum data, as encapsulated in the statistical information, is totally universal. It's the same for all systems, and it's a manifestation of the fact that in the underlying classical system you have gone ergodic. In this statistical sense, there is thermalization, but you wouldn't be able to write down the distribution of the density operator. Okay?
For a localized system, the level statistics will be different, though, right? For a localized system, the level statistics will be different.
Yeah, but the localized system is not ergodic.
Right, so there is an assumption there.
Ergodicity, symmetry is an ergodic regime. Right, absolutely. About localizing systems, we can talk later. But, So that is one thing. Now notice I always talked about some correlation functions, computer and so on, such nonsense. So the question, of course, is then if all these systems are experimentally, I mean numerically, have the same correlation functions, is there a way to get these correlation functions such, for example, analytically? And that idea came up also rather early, gaming 6-7 decades ago. So what people were trying to do is to come up with a reference model system, I mean, which is described in terms of some Hamiltonian, mimics the behavior of ergodic quantum systems in such a way that you do get these correlation functions shared by all others and analytically. Yeah? So the question is, can we come up with a designer constructed ensemble which actually shares its behavior with all these quantum systems we can discuss experimentally? And the answer is affirmative. You can do that, and I'm telling you now how it goes. And the buzzword is Fermat. So the analytic approach does the following. We construct, or we aim to construct, an ensemble of Hamiltonians subject to a few following rules. I mean, there are a few rules in the game in which we use to construct this ensemble, and then we get going. So what we want to do is, first, we want to work in a finite and fixed dimensional Hilbert space. So we impose the dimension, the matrices of our ensemble should be of finite and fixed n. Yeah, that's one thing. So second, we require a fixed average level space. So we want to construct an ensemble which has fixed n and fixed delta on average, in an average sense. We also fix the symmetry. We choose, so these H's drawn from our ensemble should belong to either one of these symmetric spaces. And then the most subtle and most important fourth condition is we invest no further information. So we do not want to invest any information beyond 1 to 3. In a sense, you can think of it that our ensemble should maximize an entropy. It should be maximally ergodic ensemble. Yeah? So this is our wish list, or this is our conditional list. And now we ask, now we will construct an ensemble that does the job. And then we have an ensemble to work with, and it will be one for which we get access to these correlation functions analytically. Okay. So, by the way, what I'm telling you is extremely, in 2 years' time there will be Le Souche summer school. If you're interested, you can spend another month just on this stuff, right? So, it's extremely superficial and abridged what I'm telling you. Yeah?
So, fixing delta meaning we just fix the unit?
Yes. In a way which I described. So, what we do is, we want to, what we seek is some probability measure, some probability distribution of Hamiltonians, which then defines an ensemble for which I can calculate something. Huh? So, how do we do that?
Excuse me?
Yep.
Is this complete now? Is this?
Yeah.
So so I'm looking at this expression you have written.
Yes, later, when I have my ensemble.
R of epsilon?
Yes.
I understand if you are looking for a quantum that these things are understandable. But if I have different dimensionalities,
yeah,
disordered systems, let's say 1D,
yeah,
2D, 3D.
Yeah.
So does it mean that this object will be the same?
Yes, in the ergodic. So you do the following. You take a finite piece of wire, or you take a cube.
So you get the same
yes,
R of epsilon.
a multi-channel quantum. some quantum wire, and then you wait before you are, you have to wait up until the time where you are in the ergodic regime. So there's some absence of localization here, and you put a wave package in here, and at some point it will have explored the entire environment.
I'm thinking of these G plus and minus. If you multiply them, take their averages, they show different properties in different dimensions.
Not if
For
you
instance,
go
1D and 2D,
No.
they should diverge.
not if you go to low energy scale.
Oh, okay, you
And
consider
if you, what I need to do is this epsilon sets the time scale. I mean, epsilon inverse is the time scale, right? And I have to wait up until the point where my time scales are so large that I have gone ergodic.
so there will be cutoffs in the
Yeah, there will be crossovers. And here, for example, I would have to wait for up until time such that I'm on time scale larger than the diffusion time, here, which can be different, and then I'm in the universal field. And there will be the same for all these cases. On higher time, higher energy scales, we get different things. So that was that. Okay, so few remarks on how this is done in practice. We have our conditions 1 and 2, these two fixations, and we can express them in terms of one constraint, which we will impose on this one here. Namely, we require that our Hamiltonian trace, if you take the Hamiltonian squared, yeah, then in an eigenbasis you will get the square of all energies. Huh? And that on average, if you then average this over our ensemble, and averaging means integrating over P over HDH, that should be fixed. It is on dimensional ground, it's some energy scale, let's call it lambda, we call it lambda squared, right? So that it defines the width of the spectrum of our model Hamiltonian. So width of spectrum. And once we have done that, our level spacing will be of order lambda over n. Right? And now we have sort of set or introduced an average level spacing. And this here we will impose as a Lagrange multiplier if you want, subject. Okay, now we have this constraint. Now you can ask yourself, how will our ensemble look like? And what will? And you could ask yourself, I mean, or maybe too many people know the answer, but what would be a good distribution, which is maximally innocent? No? Gaussian. We choose our matrix elements P of H independently Gaussian distributed with equal variance. And no, that's independent is equal, yes. So a good guess would be P of H dH equals x minus. Now the width of the Gaussian wave is kind of dictated by this condition here, and it happens to be beta n over lambda squared trace h squared. And this beta is the dimension, it's a numeric parameter which depends on our chosen symmetry. And it assumes the values 1 and 2 and 4 respectively. It's just, this is a detail. I mean, okay, so.
Is this to get the right normalization? Or
yeah.
The beta? Or?
If you play, I mean, in class A1, yeah, your Hamiltonian is symmetric. And if it's symmetric, not all of these, if you do this multiply out here, then you get dependencies. I mean, and so these are compensated for by this. So that you, but you can also call it the historic convention. I mean, who cares whether we are dealing with lambda squared or 2 times lambda squared? It's really not too important. But everybody does it in this way. So. Yeah. Okay. Now, this looks a bit ad hoc, right? Like Gaussian, I mean, maybe there are other conditions. And, so you can make the following statement. We can derive this here in more intelligent ways than just guessing. What you can do is, I'm mentioning as a side remark, you can ask yourself, what is the distribution of P which maximizes the information entropy, Shannon entropy, P log H, subject to this condition? You pose this condition and ask what would be the maximum entropy distribution, maximally disordered entity system. So the Gaussian does what we want to do. Now we have a Gaussian distribution for H, and we can ask ourselves, can we actually compute in this Gaussian distribution such objects here? And the answer is affirmative. So let me very briefly tell you what, again, the subject of the school on its own, how random matrix people, this is the defining distribution of random matrix theory, right? We're dialing up random matrices subject to distribution. So that is
Question? Question?
Yeah?
So this H belongs to a specific symmetry class?
Yes.
And I can construct this H with some given random matrix.
Exactly. You do the following, what you throw in here. H is element of UN, ON, no, what am I writing here? Excuse me.
I'm in the sum.
So this is H dagger equals H transpose equals H, and here we have H transpose equals sigma Y, H sigma Y.
And my question is, I can write these matrices on a computer with some final size and draw this distribution.
Right, you take.
Am I going to get Gaussian? As n goes to large.
No, this tells you if this is a Gaussian distribution by definition.
Yes, this is a Gaussian distribution. What I'm saying is that I can construct a Hamiltonian with these symmetric properties, and I can put it on a computer and calculate energy distribution.
But then you have to sample from some random. Yeah, right.
Yeah.
Yes, exactly, and you will get.
Gaussian.
No. What you will get in this way, I mean, you will get spectra and eigenfunctions and all that. And these spectra and eigenfunctions and all that have precisely the same statistical properties as those you would get from such a model.
Okay.
That's universality. And it has been, there is a name to it, it's called the Bohigas-Giannoni-Schmidt conjecture. It's a conjecture, it has been a conjecture. It was formulated in the early 80s that all chaotic quantum systems, chaotic regime, share their universal properties with random numbers. Right. So what do random matrix, in random matrix theory, how do people actually get access to such control exponential? I just want to give you the idea of how it's done. So idea of RMT approaches. You do the following. Suppose I want to compute now the expectation value of any operator x. And x of course should be in some operator, Hamiltonian in some way. Then it is by definition, it's dh, p of h, and then x of h. Right? And dh is a flat measure of Hermitian matrices, only constrained by this condition. You integrate over all matrix elements independently, subject to this weight, and see what you get. Now, there is one striking simplification. That's of course a formidable integral in general. But notice that this here has a nice property that's an invariant ensemble. Invariant in the sense that if you conjugate h by unitary transformation, the trace h squared remains invariant. Yeah. So that means you can always you can choose a basis here where h is diagonal, right? So let's write our h as U diagonal matrix U inverse. Right? All our h's can be diagonalized. And what we can do is, instead of integrating over H, we can integrate over all diagonal matrices and all unitary transforming matrices. So we do a variable change from this flat matrix to a polar representation. It's like polar coordinates. Now if you do that, then you have to integrate over all diagonal elements. You have to integrate over U. Then our distribution, quite strikingly, depends only on the diagonal matrix, because this is invariant under unitary transformation. So it becomes a lot simpler. It's a Gaussian product of Gaussian scalar weights now. Our distributions, if you look at them, our observables.
That's not the same P. There is.
It is the same P.
It is the same P.
It is the same P. Because if you write here U, D, U inverse, U score. It's an invariant distribution. That's the whole idea.
Yeah.
Now, I'm focusing here on observables which are invariant by themselves. So let's look at this. The green trace of a green function. The trace will kill the unitary matrices. I take the trace. Same here. So we are focusing here on observables which are invariant in the sense that they depend only on eigenvalues. Yeah. That's a restriction. But under this restriction, just a second, I can write this, and that's all. J of T. And the Jacobian depends only on the diagonalizing matrix. The technical keyword here is fundamental determinants, which is here. But yeah.
Two questions. The first is, it looks like your maximum entropy construction is essentially a canonical construction. Could I imagine doing a microcanonical construction where I demand that the maximum minimum eigenvalues of H are fixed, and would you get the same answer?
Well, yes and no. I mean, first, my understanding is it goes canonical-like when you impose this constraint. But what you can also do is, I mean, maybe that helps. Instead of working for H, let's work in terms of scattering matrices. I cook up an ensemble of e to the IH. Right? I say that such system can be described as a scattering matrix. The scattering matrix has the same universality as time evolution e to the IH, and then I want to impose a measure for scattering matrices. And that would be a flat measure, so there will be no constraints. It's not exactly, no, you were really asking about microcanonical distribution. I take it all back what I said. No, I don't. I think that's what we have here. I mean,
so here, I mean, the total size of the spectrum fluctuate a little bit.
Yeah, a little bit, exactly.
But does it really matter? Is that
no, they are very weak fluctuations.
Okay. And then the second question is, when you do this diagonalization and rewriting it, are there no restrictions on the unitary matrices that diagonalize it?
Oh yes, there are. There are. In the orthogonal case, these should be taken from the invariant scope. Indeed, yes. I mean, if this is a matrix, you get away with orthogonal matrices. Yeah, sure.
And then on this last line, the integral du, there's nothing dependent on u, so it's just a constant.
That gives you a constant, yes. It's just the volume of the unitary scope.
Just notation, this is x dot of u or x hat?
No, that is x hat. All right, so that here essentially, that here is gives you a constant. And this is a bunch of, it's now no longer order n squared, but n integrals, and you can, for typical observables, you can just do them. There's a whole mathematicians like this stuff. I mean, there's a whole machinery. Keywords, in case you have heard them, are orthogonal polynomials and all that. But you can do these integrals for most observables, right? And I'm telling you now what you get, the results for these two guys here, if you do the integral. And what you get is what you saw before numerically on your computer. but I'll make an analytic one. So, R and T correlation functions. So let's begin with rho of E, the density of states in your random matrix ensemble. I mean, you plug this here in and see what you get. And what you get is somewhat funny. It's the famous Wigner semicircle. Pi lambda 1 minus E over twice lambda. So you have a semicircle of extension of this extension. This is a typical so-called mean field result. Indeed, there are little details here. Let's forget about them. Now look at this. I mean, this is your density of states in your random matrix. Now, who has ever seen a real quantum system with a semicircular density of states? I mean, it's somewhat of an artifact of this approach. The philosophy in which we will kind of work with this is we're essentially interested in statistical properties of spectra. I mean, really correlations and stuff like that. Not so much in the average density of states. The average density of states, of even of a nucleus or a piece of metal, will never be exactly constant. So even of a real system, there will be some systematic dependence on large scales in the density of states. So the way we look at these systems is we zoom in into a finite portion of the spectrum, like here, which can be still macroscopically large, and then look at correlation functions for finite, possibly very large number of levels. Right? And you can think of the scaling. We send the dimension of the matrix, we can send it to infinity, we get more and more levels which cluster here, and we then look at statistical properties up here. Some of the idea here. Okay, much more interesting is the two-point correlation function, R2 of epsilon. Yeah.
How do you get this? So
I tell you, we will discuss it.
Okay.
This we will derive. Yeah.
So, suppose we were using P of H, which is not Gaussian, but some other thing, only it's kind of flat near H equals 0.
Yeah.
Then we probably get the same results, right?
Yeah, not for the. Okay, actually, a colleague of mine, a mathematician, just get a very, very prestigious chair for answering that question. So you can play with other invariant ensembles, which still have invariant in the sense that they're unitarily invariant, but no longer possibly Gaussian. And the one-line summary of what then happens in general is that the average density of states can well look different. But the correlations in the band center, if you zoom in, remain invariant. And yeah.
So zoom in means that you take n to infinity.
Yeah. You can do a kind of limiting procedure. You define a parameter epsilon over level spacing that you keep fixed, and then you send n to infinity. That's a typical scaling procedure.
So is this relevant to approximating around Fermi surface?
Yeah, for example, you put in a metal, say if you have you press the metal and plot the density of states, and you get, depending on dimension, you have some average density of states which increases in some power law manner. Then you zoom into some finite region where you no longer systematically see this increase, and ask for statistics here.
So if you properly analyze this, can you go from this zooming into 0 to zooming into Fermi?
Yes, the key word is, in random matrix theory, nuclear theory, this procedure is called unfolding procedure. You kind of rescale your spectra such that on average the density of states is constant in the window where you look at the system. Yeah. Right. So, this is now the two-point correlation function where I introduce a symbol S. And S is simply, it's again a standard notation in the field, is epsilon measured in units of the average delta. Delta average is the average density of states here, which happens to be pi lambda over n. So that is the inverse of the density of states here. It's this beast, it's the average level space in the band center. Then we rescale out in these units and multiply by pi, and out comes the dimensionless parameter S. And that's it. These correlation functions now depend on this dimensionless parameter. And what you find is that in the A case, in the unitary case, first, this is 1 minus sine squared S over S squared. That's an analytical sign. And in the other cases, say for A1, you obtain 1 minus sine squared S over S squared. I'm just writing it for illustration so that you see that something changes here. So S squared, integral S to infinity, sine squared S prime over S prime squared ds. So not very inviting formula, some integral representation. All I want to say is the result changes depending on where you are, in which symmetry class. It's a universal function of this S. I mean, it's the only dimensionless parameter we have. And pretty much that's it. What is the physical meaning of this? You can understand it as follows. There is, you see, if you send S to 0, right? If you go to very, very small energy, this asymptotes to 1. So your two-point correlation function goes to 0. And what this tells us is that in a chaotic system, you will never find two infinitesimally neighboring levels. They repel each other, so if there is a level here, there is with certainty none very close by. That's called level repulsion, this phenomenon. And yeah. So in a chaotic system, if you have a finite density of states here, you will not have a finite density of states here. That is, they like equally charged charges, they repel each other. And that reflects in this two-point correlation function in a vanishing of this product if you go to energy scales much smaller than the level space.
Well, R goes to 1, right?
No, R goes to 0.
Oh, 0.
Because that goes to 1. In fact, there is a delta function at 0 sitting here, which I swept under the rug. So this has the same behavior down here. And that's pretty much what you get. And from this formal way of doing this integral. Was it fish?
Is the choice of the distribution in terms of having maximal disorder based on data in the ergodic regime?
What?
You said that you chose that distribution to better maximize the efficient entropy.
Yes.
That's maximally disordered. Was that based on given the ergodic regime?
Yes, sure. Yes. It's more or less the definition of the ergodic regime.
How do you know? But in the ergodic regime, the system also remembers the symmetry. And how do you know?
The symmetry, yes.
The symmetry doesn't induce correlations.
No, it does. It quite vitally. I mean, because there was this was on this blackboard, I maximized entropy conditional to the symmetry. The symmetry is in condition, and that reflects in different profiles. I mean, they're not dramatic, these differences, but they are there, right? Yeah.
One expression. Is it the only difference between A and A1 is just the beta coefficient here? Or?
No, the symmetry is the
yeah, then the only difference.
Yeah, here in the ensemble is only this beta, which is trivial. For A2, I don't even write the formula. It's not very rewarding. Yeah?
R2S for class A1, does that look, I mean, I can't see it, does that look like a Wigner-Zermatt state?
Oh no, that's P of S you're talking about.
That is P of S.
P of S for the other guys is the following question: given a level here, what is the probability of finding a level in distance S? And that, the answer is a correlation function known as
The next one. The next one. Not A level. Finding
the next level. Yes, indeed. The next level, precisely.
And this is A level. This is finding A level.
This here is a two-point correlation function. This is a product of two. I mean, the P of S is much harder to get analytically. Because you're asking a more complicated question about, actually you have to exclude that there's another level. more complicated.
Yeah. Does this result hold further from E equals 0 if I rescale the level space?
Yes, that is holds throughout the entire ergodic regime.
Okay, but there I would define S slightly differently. I mean, if I were to go at, I don't know, lambda, and E equals lambda instead of
No, well, no. With conditional to the scaling procedure, you always have to be in this unfolded. I mean, no, actually, if you, no, I take it back. You can unfold the entire spectrum over the entire semicircle, and then it holds through the entire range. Here, but that's not a very rewarding statement like, from a physical perspective. The physics here is these correlations will be observed. I mean, the natural high energy cutoff is the limiting inverse of the time scale where you leave the ergodic regime. Yeah? Once you're out of the ergodic regime, this breaks down. But within the ergodic regime, we have this. I mean, in the sense that S is an energy scale, and that is the inverse of the time scale, and that time scale has to be larger than this ergodic limiting time. Okay.
I guess what I'm asking is, there's always some dispersion in the, there's always some fluctuation in the density of states, and in the same way you were using this unfolding procedure to kind of locally flatten the density of states around E equals 0,
yes.
It seems like I could do the same thing in random matrix theory
Yeah.
around E equals lambda,
Yeah.
as long as I just rescale my
Yes,
delta.
exactly. Yeah.
Is that
Right.
fine?
Yeah.
Okay, so I
Mhm.
Just to make sure, this parameter beta labels exactly the number of independent parameters you put in your Hamiltonian, right? Number of independent matrix elements. Is that right?
So there's zillions of independent metrics.
So, but I mean the difference between beta equal 1 and beta equal 2.
You mean the factor of independence?
Yeah. So in beta equal 1 you have
no,
twice
I'm actually
more.
not quite sure. That's I have to do the counting. But when you work with the symplectic class, you have to these can represent in terms of quaternions. What? Quaternions. And maybe you're right, maybe not. I didn't do the counting. But beta is it's important parameter, but not for me so much.
I think that beta ordering 1, 2 is like 2, 1, 4.
You're right. You're right. You're absolutely right. Yeah, I got it wrong. Sorry about it. Yeah. Okay.
You say it breaks down at short times or long? Smaller?
At short times.
At short times it breaks down.
Yes. When you know.
Okay.
So we started surely 15 minutes late, didn't we? And I owe you time from yesterday. Okay. It's a disgrace. So let me tell you what I want to do next. I won't do it now. This is all nice and fine. Let me before I tell you what I do next. Let's summarize a few salient features of these correlation functions. First, I maybe stressed too much already. I mean universality here, but also observe that these results are non-analytic in S. Yeah, so for S equals 0, these are not analytic around S equals 0. So in the long time limit, there is non-perturbative stuff going on. That's what it's telling us. I mean, it's a hint that there is non-perturbative physics, which will not be accessible in whatever perturbation theory you could do based on a perturbative expansion of your green functions. That we observe. And the notes are actually copied, and I don't need to write this down because you will get them. So I'm just telling you. Universality, non-analytic around S equals 0. For large S means relatively short times. I mean, energy is much larger than the level space. You can do perturbation theory. I mean, at least looks like it. Suppose S is very large, and the sine squared averages to 1/2, right? And then you get a nice 1 over s squared here, essentially. And it's the same down here, in fact. You don't see it with your naked eye. But there should be, that hints at the possibility of doing perturbation theory in a relatively short time regime in this sense. Some perturbative expansion should be possible, and we will get there. And yeah, I already mentioned this level repulsion. So what I want to do next is something very stupid. We will re-attack this problem. I mean, we will, but not in the language of this integral which I wrote down, which is nice and exact, but doesn't tell you what's going on physically. So I will try to rederive as good as I can these results in terms of a diagrammatic perturbation theory. So we will formulate a perturbative diagrammatic, Feynman diagrammatic expansion of these correlation functions for our random matrix. Now you can ask, why the heck? I mean, what is this going to tell us? We will do far worse than these results. We will only obtain some high energy asymptotics in this way. And nevertheless, this is a very instructive exercise for 2 reasons. Reason number 1 is we will discover a lot of structure in these Feynman diagrams. So there is some kind of, you will see a structure unfolding in front of your eyes in the diagrammatic expansion of the random matrix ensemble. And that structure is again, hints at as always in this game, it's some huge degree of universality. What's important about this structure, it gives us a hint as to the structure of more advanced theories beyond random matrix theory. Because random matrix theory is nice and fine, but it is very restricted in its scope. It's just confined to this ergodic regime, but we definitely want to go beyond that. At some point we want to describe insulators and quantum Hall systems and whatever, which are definitely non-ergodic, but still influenced in their behavior by symmetries. So a clue as to the shape and structure of these theories we can obtain from the diagrammatic reinterpretation of these results that will tell us how to advance and go beyond the realm of random matrix theory. That's why we are doing it. That's one reason. The second reason is the diagrams I will construct are very universal in their own right, in the following sense. We will do a diagrammatic theory for random matrix ensemble. But you could also think about, say, you could be interested in disordered metal and do Abrikosov-Dzierżynski diagrams there. Or you are interested in a chaotic quantum dot and apply Gustav-Leif formulas and play with periodic orbits. In either case, you get diagrammatic expansions, right? So we are Hamiltonian. The details of these diagrams will differ, but their raw architecture, the structure, the topology of these diagrams will be the same in either case. So these diagrammatic expansions, they constructed for rather different, microscopically rather different systems, they share a huge degree of similarity, and this similarity is best exposed in the simplest model we have, and that's random matrix theory. Okay. So that's the motivation for going a bit diagrammatic. I mean, it will not be a big deal, it will be just a few pictures we will draw. And from there on, we can then go into, move on towards field theoretic formulation tomorrow. Okay, thanks.